So previously we looked at one example where we did our molecular species balance and our atomic species balance. So I think this was the example, chlorination of methane, where we have the feed and then we find the product composition. So if you remember in our previous class, we did mention that the rule of thumb when we have a simple system or only one reaction for the system, it is easier for us if we use molecular species balance. But if you have more than 1, 2 or 3 equations or reaction, it will be easier for you if you solve using atomic species balance. So today we'll be looking at another example where we actually have two reaction happening simultaneously. So the question is that methane is burned with air in a continuous steady state combustion reactor to yield a mixture of carbon monoxide, carbon dioxide and water. The reaction that takes place are CH4 plus 1.5 oxygen will give you carbon monoxide and water vapor, and CH4 plus oxygen will give you carbon dioxide plus water vapor. So if you look at this equation, this is actually your combustion equation, the topic that we cover after this. So for this type of equation, if you have CO forming and CO2 forming, so we can say that this one is known as partial combustion and this one is known as complete combustion. So for our case here, since we have two equations here where partial combustion and complete combustion is happening, so it will be easier if we use atomic species balance. So the information given, the feed to the reactor contains 7.8 mole% of CH4, 19.4% of O2 and 72.8% nitrogen. And then the percentage conversion, our conversion percentage of methane is 90%, and the gas leaving the reactor contains 8 mole of CO2 per mole of CO. So calculate the molar composition of the product stream. So we want to find what is the composition in our living gas. So we have, this is our conversion value. Okay, we have this value, and this one 8 mole of CO2 over CO, we can say this is our selectivity. So these two informations are crucial for us to use. So now we know the basis and we know almost all the information given. So the first thing we need to do is that we need to draw our process flow diagram or flowchart. So this is our combustion reactor. We have feed coming in. Okay, we have feed coming in. So we say that our basis was 100 mole. Okay, 100 mole of feed. And in that 100 mole, we know that 7.8% is methane. 7.8% is methane, CH4. And then we have 19.4% is oxygen, O2. And then the rest, 72.8% is our inert nitrogen. Okay, and then we know that since we know the conversion, so we know that there's going to be unreacted methane in our product stream. So we'll have CH4 unreacted, oxygen unreacted, and then we'll have our product which is CO, CO2, H2O, and also inert nitrogen. So this is the composition in our product stream. So since we don't know any other information, we can just say that this is, we can label N1, N2, N3, N4, N5, and N6. Okay, so we have 6 unknown. So since we have two equations, so we'll be using atomic balance species. Okay, atomic species balance to solve our problem here. So first of all, let's look at what other information is given to us and how we can use that information. So the first information given to us is that we know that the percentage conversion, right? We know that percentage conversion is equal to 90%. So meaning that 90% of our feed of methane is converted and the rest 10% is unreacted. So we know that the formula of percentage conversion is equal to mole reacted over mole reacted over mole fat times 100. So this is our formula, and we know that the mole reacted here will be whatever our methane is consumed. So we can say that whatever is consumed is that the initial mole minus the final mole. We can say that, so 7.8% times 100 is we're gonna get 7.8 mole. So 7.8 mole. So the amount left in our system here is gonna be N1, as we explained in our previous example, and then divided with 7.8 times 100 is actually equal to 90. So straight away we can get N1 is equal to 0.78 mole. So we have found the value of N1 here, right? N1 we have found. So the next thing that we were given was the ratio, the selectivity between CO2 and CO. So we were given that the ratio of mole of CO2 over mole of CO is actually equal to 8, right? So this one is also, since this is mole CO2 and mole CO only appear in our product stream, and we have labeled them, so CO2, as N3 and N4. So I can just write here N4 over N3 is actually equal to 8, and N4 is equal to 8 and 3. So we have another equation here that we relate the mole of CO2 to mole of CO. So now those are the only information that we have. So we can start our first balance on carbon. We say that we do balance on carbon. And then remember, we only have carbon, hydrogen, and oxygen in our system. So if we look at our equation here, we have carbon, oxygen, and hydrogen in our system. And when we are dealing with atomic balance, it is most easier for you if we just look at whatever you have in the input side and whatever you have in the output side, because we say that whatever atom we have on the input side will equal to whatever atom we have on the output side. So once you have labeled your flowchart, then you can just look at here. So in my input side, okay, so I have 1 mole of carbon in every 1 mole of CH4, right? And I already know that the mole of CH4 is 7.8 mole. Okay, and then that is the only carbon I have on my input side based on my flowchart here. This is the only carbon that I have. And then next one, I looked at here, I have the carbon in my unreacted. Okay, so I have carbon on my right hand side here, which is my unreacted methane. So I can put here 1 mole of carbon again in 1 mole of CH4, and then I know that I've labeled that as N1. Plus I have carbon in my CO, so I can put here 1 mole of C in 1 mole of CO, and then I know that the mole for CO is N3, plus I know that I have C in my CO2 molecule, so I can put here 1 mole of C in 1 mole of CO2, and the mole here I've labeled as N4. So if I were to simplify and try to solve the equation, I'll get 7.8 is actually equal to N1 plus N3 plus N4. And I already calculated my N1, and I have a relationship between N3 and N4. I can get here 7.8 is equal to N1 is 0.78 plus N3 plus I know that N4 is equal to 8 and 3. So I can just put here 8 and 3. And solving this, I can get the value of N3 is equal to 6.24 mole. Sorry, no. The value of N3 is 0.78 mole. Okay, and then N4 is actually equal to 8 times this value, and I'll get 6.24 mole. So I've gotten the value of N3 and N4. The next thing that I can do is that I can do balance on oxygen. So balance on oxygen. So on my left hand side, on my input, I have 2 molecules of oxygen per every one. I have 2 atoms of oxygen per 1 molecule of oxygen gas. And then I have here the mole of oxygen gas is 19.4, right? So the same thing I'm doing here, but I'm just not writing the mole of C, mole of here. So I have 2 mole of oxygen in 1 mole of oxygen gas, and this is my oxygen gas mole, because this is where we say that 19.4% out of 100 is 19.4 mole. So that is the only oxygen I have in my input side. It's equal to, now if I look at my output side, I have 2 atom or 2 mole of oxygen in my 1 mole of unreacted or leftover oxygen molecule, and then I have labeled that mole to be N2, plus I have oxygen in my CO. So 1 atom of oxygen in 1 molecule of CO. So 1 plus my N3, right? This is my mole of CO, plus I have 2 atom of oxygen in 1 molecule of CO2. So 2 times N4. And then finally I have 1 atom of oxygen in 1 molecule of water. So that is going to be my N5, right? So if I were to simplify this equation, I'll get 2N2 plus N5 is equal to 25.554. So this is my second equation that I have. So in order for me to solve this equation, I will do balance on hydrogen. So hydrogen I have in my input side, which is CH4. So I have 4 atoms of hydrogen in every 1 molecule of methane. So times with the mole of methane, which is 7.8, is equal to, okay, that is the only hydrogen I have on my input side. So I have on the output side, I have the unreacted methane or leftover methane. So in there I have 4 oxygen, and the mole is N1. and then the only hydrogen I have is in my water molecule. So I have 2 hydrogen atom in one water molecule, so the mole is N5. So I already know the value of N1, which is 0.78, and then I can substitute that value and I can find the value of N5 is equal to 14.04 mole. Now that I've gotten the value of N5, I can put it here in this equation and I can find the value of N2 is equal to 5.75 mole. Okay, so I've gotten if we go back to our flowchart, I've gotten the value of N1, I've gotten the value of N2, N3, N4, N5. The only left is N6 for my nitrogen. So if you were to do balance on nitrogen, so we know that for nitrogen gas, it is inert. So if it's inert, balance on N2. So if it's inert, input is going to be equal to output. So whatever amount of nitrogen gas we have on the input side, we'll have the same amount in the output side. So we can just say that N6 is actually equal to whatever value we have, which is 72.8 mole. Right? Because in our flowchart, we said that 72% out of 100 is 72.8 mole. So that is how we calculate using atomic balance for reaction that for questions that we have more than one equation.